Welcome to DC Review Part 1. This is not designed to be professional, but it is designed to be informative. These are must-know topics for industrial electronics. I'm going to start with the concept of a voltage drop, where we have a resistor with conventional current flowing through it that produces a polarity in this sense. Voltage drop is the voltage across the resistor. It does not necessarily mean it's referencing ground. I could have a resistor in my hand that had 100 volts drop across it, and that wouldn't tell you anything about the voltage if you connected the negative lead of a meter, say, to a water pipe. A voltage rise, on the other hand, and I'm showing here a battery, which is more than one cell, is when conventional current flows into the negative lead of that device and out the positive lead, and that's called a voltage rise. So in circuits, the sum of the rises has to equal the sum of the drops. Now, Kirchhoff, in German, his name is Kirchhoff, so if you hear that, it's the same thing, basically says that the sum of voltages around the loop have to be zero, and I kind of like this form a little bit better. It's a little bit easier for me to understand. If you are referencing ground, we need to speak about this. All it is a common point, and these are two different symbols for it. Now, in your automobile, it's 12 volts negative ground. In most electronic equipment, ground is going to be the negative part of the power supply. But if you like to collect old cars, say pre-1955, they have positive grounds, or at least some of them do. And if you take a voltmeter and measure relative to a water pipe what's coming into your home from the telephone company, one wire will be close to zero and the other wire will be close to negative 48. So ground is just a reference point. It can be connected to earth or not. It can be just a chassis or a foil trace. It's where you would put the negative black lead of a multimeter. So if you're involved in a test situation, making sure that this is true is a safety check to make sure that you didn't make a mistake. The sum of the rises has to equal the sum of the drops. Let's go on here. Here we have a simple circuit, and I'm showing this as a power supply instead of a battery or a cell. Positive and negative. I have a ground here and three resistors, and the nodes or net names are A, B, C, and D. And what we see to the left side of this arrow is a voltage rise, because conventional current, as you see in red, would be flowing in this direction through the power supply, and the voltage drops are on this side. Now, it is always a good idea to push a current arrow through these and label the drops plus to minus. Always a good idea to do that. So in this simple circuit, we have three resistors, a 12 volt supply, and our mission is to find the voltage drop across the resistors. So some people come out of DC are very comfortable with pushing currents. You need to learn voltage divider. So here we see the voltage across VR1, that's this guy, is 12 volts times the resistor that we want to find the voltage across, divided by the total resistance, which in this case is the sum of these three, which comes out to be 10.2K. And if I were to measure the voltage across this, I'd find it to be 2.59 volts. Likewise, using VR2, the only thing that changes is the numerator. And in finding VR3, the only thing that changes is the numerator. And here we get 5.53 volts, and down here for the 3.3K, we end up with 3.88 volts. Now, if I'm doing this and I'm turning in a test, the check is to add up the drops, and they ought to equal the rises. If they don't, you made a mistake. Find it and fix it. So voltage divider is the key here. If you don't know it, learn it, be comfortable with it. It's a tool set that you need in your belt. It's your friend. Now here we have a circuit, and we're going to be introducing what are called doubly subscripted variables. And my purpose here is to find the voltage between point B and point D, which is effectively ground. Yeah, it's supposed to be a ground symbol. There's a little better there. And if I decompose this, what I do is I take the first variable and I subtract the second variable. So this could be VB, also VB minus VD. So all you do is subtract the second variable from that of the first. And if it's unspecified, like this is a singly subscripted variable, it is assumed that the second variable is ground. So to measure VB, D is the same as measuring VB to ground. Everything is really a doubly subscripted variable because DMMs have two leads. So to do this, I'm going to use voltage divider again, only this time in the numerator I'm going to include these two resistors. This works if the resistors are adjacent to one another, and I find that that voltage comes out to be 9.41 volts. So if I want to find now VAB, that's the voltage across the 2.2K resistor, I would take VA and subtract from it VB, and remember these are relative to ground. So we'll have 12 volts relative to ground minus the 9.41 volts we just determined was at node net name B, and that'll give us 2.59 volts across this resistor. And do note that that was the same as what we got in the voltage divider before. Now suppose you're asked to find VBA. Nothing's different. You take your first subscript and you subtract from it the second subscript. So VB is going to be 9.41 volts minus 12 volts, and your meter will indicate negative 2.59. Now in this case, the negative lead of your meter will go on point A, and the positive lead will go on point B. And that'll give you the negative 2.59 volts. Why do you want to do it backward? Well, depends. It's a circuit analysis tool. Now if we go to find the current, which is fairly straightforward, it's just 12 volts divided by the sum of the resistors, and that comes out to be 1.8 milliamperes approximately. And if we were to push this current through each resistor and find the voltage drop, it would come out to be very close to what we determined on the previous page. So doubly subscripted variables are going to be something you're going to be seeing a lot of. Now, if we start out with the three basic equations for Ohm's Law, and to my surprise, a third semester student misfired on one of these. I'd like to think it was a mistake. These are the formulas you have to know by heart. And also the power formula, since we're in a power electronics course. So we'll start out with P equals V times I, and then we'll do a little substitution here. And our substitution will be that I will be substituted with V over R. So what we end up with is V times V over R, or V squared over R, and the unit is watts. The other method is we have P equals V times I, and in this case, for V, we're going to substitute I times R. So we end up with I times R times I equals I squared R. Now what you don't want to have to do on a test is to manipulate these things and figure out what they are. These three formulas here, this guy, and this guy, need to be memorized. You need to know them like the back of your hand because you're going to be using them a lot. Now power is the rate of energy conversion, and I'll be speaking to that in a little bit in the future. So that'll do it for DC Review Part 1. And we'll follow on a little bit more with some somewhat advanced topics. Thank you for watching, and make sure you understand the content.